Innovative energy management system for smart buildings and grid interactions was a project started in December 2017 at the Electric Power Engineering Division of Chalmers and continued for 2 years. The project was funded by Gothenburg Energy through Gothenburg Energy Chalmers Collaboration Framework. And the project was implemented at the HSP Living Lab. The role of buildings in the energy system is changing. They are becoming active players of the energy system. By controlling the energy resources and the controllable loads within the buildings, it is possible to provide flexibility for the distribution system. Various factors are promoting this change. Smart readiness of buildings has increased significantly during the past years due to the usage of innovative technologies, which facilitate communication and interaction among the devices and the users. Also, the increasing integration of controllable energy-intensive loads has increased the flexibility potentials of the buildings. The objectives of this project was to develop a building energy management system for the HSP Living Lab, to engage the inhabitants of the building in energy management, and to reduce the overall energy costs. We call this energy management system BEMS. Also, another objective was to investigate the provision of different grid support services from the buildings. So a close to real-time energy management system was needed to control different resources in the building. Validation of BEMS at the HSP Living Lab would also be required to show the performance and the effectiveness of the solution. HSP Living Lab is a multi-family residential building with an advanced measurement system and provide access to data from smart meters and sensors. But in the year 2017, when the project started, the energy system of the building was not controllable enough to provide demand-side flexibility. So the first phase of the project was to study the possible solutions to increase the flexibility and the controllability of the building. The solutions were to add new energy system and loads in the building and to improve the control system of the existing loads. So at the end of the project, the HSP Living Lab has converted to an energy flexible buildings. Now in year 2021, the building has an integrated energy system composed of various controllable electric and heating systems. And the BEMS has the possibility to control different energy systems in the building. As part of this project, 2 air-to-water heat pumps and 3 hot water storage tanks were added to the heating system of the building. An electric vehicle charging station was installed in the building, which enables the inhabitants to charge 2 EVs with 32 amperes simultaneously. And also the controller for the washing machines were designed that can delay the operation of the washing machines. By installing the heat pumps in the building, the electricity and the district heating system were connected to each other. This enables us to study the interactions of these 2 different energy carriers on each other. BEMS is designed to minimize the total energy cost in the building and reduce the peak demand. The operation of controllable energy sources in the building is managed by BEMS close to real time. BEMS sends the optimal control commands every 5 minutes. However, in each iteration of decision making, a 24 hours time horizon is considered. The decisions are made based on the forecasted data for the electricity and heat demand. For the loads like washing machine and dishwasher, the user's preferences are received via an interface. In order to make decisions for every 5-minute intervals, a longer time horizons is considered. Decisions are made iteratively in a looking forward multi-period framework. And the main decisions are composed of the charging current of the electric vehicles, the charging and discharging power of the battery, which is coupled with the PV, with the photovoltaic panels in the building. And the operation of this heating system is also controlled by the BEMS. BEMS determines how the heat demand is served by the district heating system and the heat pumps. Finally, the delay in the start time of the uninterruptible loads, such as washing machines, are determined by the BEMS. The input data to BEMS are the preferences of the users, which considers the comfort constraint of the users, signals from the utility, which could be price for the energy and demand response program, the forecasted values for demand and PV production, the built-in parameters of the devices, and also the measurement data obtained from the sensors. So the BEMS at the HSP Living Lab is composed of different components. It includes load shifting of washing machines, controlled charging of the electric vehicle, control of the battery energy storage system, and the heating sources in the building. It also includes forecast algorithms for the PV production, electricity demand, and heat demand. And visualization part is also needed for the optimal operation of the BEMS. Different type of communication protocols are used for each of the energy systems that are included in the BEMS. BEMS receives measurement data from the devices and from the sensors, and also needs to send the control commands via appropriate communication protocols to different devices in the building. BEMS communicate with the controller of the washing machine via MQTT protocol, and it receives the selected washing program and the expected end time, which are both determined by the user, and the BEMS decides the optimal start time of the washing machine. It is actually the delay that each washing program could have. And the controller for the washing machine, the control system for the washing machine, is composed of different systems. And we need an interface with the user, and also one of the steps that is required for the control of the washing machine is energy profiling of the washing machine. The optimization model is connected to the controller box via Wi-Fi and MQTT broker, and the decisions that are made in the optimization model are sent to the controller box, and the user also communicates with the controller box via an LCD and rotary knobs and buttons that are on the controller, on the washing machine controller, and the user can select the expected end time for the washing program which they have selected. The washing program is directly selected on the washing machine by the user. In order to be able to determine the optimal start time of the washing program, we need to have energy consumption of different washing programs. So this is done by mapping the data from the CMIS, which are the data for the washing programs, with the energy data. The energy data comes from the smart meters, and they are the historical data for energy consumption at that washing machine. The energy profile for the normal 40 degrees washing program which has 45 minutes duration, is shown in this picture. And as we see here, washing program is composed of different steps like waiting, main wash, drain, extract, and rinse. And as shown in this picture, the main wash usually has the maximum or the peak electricity consumption, which for the case of normal 40 degrees washing program is around 2.5 kilowatts. Another washing program is the normal 60 with a duration of 55 minutes. We see different levels of power consumption for this washing program. In the left, we see the relation between the temperature of the water and the time of the washing. And on the right side, we see the power consumption. And another washing program is the normal 95 degrees. As shown in this picture, the maximum electricity consumption of this washing program is around 3 kilowatts, is close to 3 kilowatts for the main wash stage of the washing program. The controlled charging of the electric vehicle is another module of the BEMS. The user determines the expected state of the charge at the departure time and the expected departure time in a web interface which has been designed for this purpose. Also, the initial state of the charge and the battery capacity and the maximum charging current are the other relevant information that are required from the user. And then the BEMS determines the amount of the charging current. This current limit is also sent to the charger via OCPP 1.6 communication protocol, and it determines the amount of the charging current every 5 minutes and updates these charging currents for every 5 minutes. BEMS controls the charging and discharging power of the ferroamp battery. It uses MQTT to subscribe and read the required data and to publish the control commands, which are the charging and discharging power of the battery. The non-linear dependence between the state of the charge and the power is determined through various charging and discharging tests. And then the piecewise linearization is used to include this relation in the optimization model. Another control commands from the BEMS is the percentage of using heat pumps, district heating system, and also using the water storage tanks. The set points are updated every 5 minutes. The communication with the control unit of the energy save heat pump is through Modbus. The control unit also receives the supply line temperature from the KTC system. Proof of concept for the BEMS solution and simulation studies were used to show the viability of the BEMS. The integration of the BEMS with the building energy systems was tested. The solutions were tested under controlled conditions for each of the devices separately, and the simulation studies were used to validate and verify the performance of the algorithms. The behavior of the system was assessed under different pricing schemes and power-based tariffs for the peak demand. The operation of the battery is tested in a scaled-down model. 10 time steps are considered, each with 2 minutes duration. The BEMS communicates with the battery via MQTT. It subscribes to the battery, reads this OC level, then the optimization is carried out, and the charging and discharging powers are the outputs of the optimization model. The commands are finally published to the battery. The rolling horizon approach, which means that the input data for
price and demand varies in each iteration. So in iteration 1, time steps 1 to 10 is considered. Always 10 time steps are considered in the optimization, and this moves as we go further in time. The connection between the solar panel, the battery, and the consumption point are shown in this figure on the right-hand side. Also, the connection with the grid is shown in this picture. Initially, as we see in this demonstration, the grid is providing 9.8 kilowatts. 1 kilowatt is used by the battery to charge the battery, and the rest are used for the consumption at the HSP Living Lab. But when the first iteration of the optimization is solved, it decides to discharge the battery with 2.1 kilowatt, as we see here. And we need to wait for the target time period to start, and then this command will become active. So we need to wait around 2 minutes until this command becomes active. So I move to around 2 minutes, and as we see, it has started to change slowly from little by little. Okay, the battery starts to discharge, and the discharging value of the battery increases. The rated capacity of battery is 7.2, and the state of the charge of the battery at that point is 62%. Different decisions are made in the next iteration, considering the variation of the price and also the changes that we have in the consumption profile. Also, the variations of the power produced by the battery, also produced by the solar energy, and the consumption are shown in the right-hand side below, on the right-hand side. And as we move, you see different decisions are made. So in here, in the fourth iteration, it decides to charge the battery with 1,450 watts. And then, so at the beginning of the target iteration, we will observe that the battery starts to charge with this amount. So I move to that point. So the charging power starts to increase, and it reaches to 1.4 kilowatts. This model can run continuously at the HSP Living Lab and control the charging and discharging power of the battery with respect to the forecasted price and forecasted demand of the BEMS. 3 case studies have been carried out, and we added to the energy system, we added to the loads one by one in the case studies. The time horizon is 24 hours, and it is moving as we go further, and we make decisions for every 5 minutes. In the first case, we considered the battery energy storage with 7.2 kilowatt hour capacity, 4 washing machines and 3 dishwashers. The input data to this model are the PV generation and the consumption profile of non-flexible loads, and also the consumption profile of non-interruptible loads such as washing machine and dishwasher. And the BEMS begins the operation at 7 o'clock in the morning of day 6 of September 2018. The results show that the optimization-based algorithm is able to reduce the peak demand in the building for about 18.8%, and also it's able to reduce the energy cost for about 9%. In case 2, 4 electric vehicles are also considered And the user provide flexibility by allowing a delay in the start time of the washing machine and the dishwasher. The BEMS delays the operation to optimize the energy consumption in the building. Also, the electric vehicle owners provide flexibility by informing the expected departure time and the state of the charge at the departure time. The results show about 4.3% reduction in the energy cost and 24.5% reduction in the peak demand. And in the last case study, the heating system is also included in the optimization model. District heating and 11 kilowatt heat pump are both serving the heat demand. The results show 4.5% reduction in the energy cost as a result of using BEMS in an integrated energy system.